Hello students, welcome back. So we'll move on to the next method of solving the bias problem, that is penalty method of handling boundary condition. So till now we were using elimination method of handling boundary condition to solve the bar problem. Now we'll move on to penalty method of handling boundary conditions to solve the similar bar problems. Okay. So for example, if a stepped bar is given like this, first and second cross section, and it is fixed at both the ends. Now the global equilibrium equation for the above figure is Kq is equals to F. So Kq is equals to F, we can write it like this: K11, K12, K13, K21, K22, K23, K31, K32, K33. The stiffness matrix of 3 cross 3 because there will be 3 nodes here. Okay, and Q1, Q2, Q3, Q1, Q2, Q3. F1, F2, F3, F1, F2, F3 because there will be 3 nodes. Okay. So now in the penalty method, for the similar problem, for this problem in the penalty method, penalty values are added to the main principal diagonal elements which are associated with fixed nodes. So here I repeat, in the penalty method, penalty values are added to the main principal diagonal elements which are associated with fixed nodes. What do you mean by that? So here, let me continue this. For the given example, node 1 and node 3 are fixed. So penalty values are added to K11 and K33. So here penalty values will be added to the principal diagonal elements of the fixed nodes. That is what the condition in the penalty method. So here the fixed nodes is node 1 and node 3. Okay, so penalty values are added to the principal diagonal elements of the fixed nodes. See here Q1, Q3. So this is the fixed node here. Okay, so this is the principal diagonal element of the fixed node. So penalty value should be added to this K11. Similarly, penalty value should be added to K33 because this is the principal diagonal element and it is the third node. Understood? The modified stiffness matrix. So when you modify it, that's what I said. So K11 plus C, K33 plus C. Okay. So earlier this was the stiffness matrix. So now the stiffness matrix is this. Penalty value is added to the principal diagonal elements of the fixed nodes. So this is a fixed node. This is a fixed node. Here node 1 and 3 is fixed. Okay. So principal diagonal elements of 1 and 3 will be penalty value is added to the principal diagonal elements of 1 and 3. So what is this penalty value? Penalty value, we have the formula C is equals to maximum of Kij into 10 power 4. That is, Kij is this one. Anything, Kij, Kij, Kij. Okay. Any maximum value in this matrix will be the Kij. Into 10 power 4 will be the C value. That C value you have to add to this. Okay. Next, also modified force vector. So when the stiffness matrix is modified in the penalty method, the force vector also modifies. So F is equals to wherever you add the C, wherever you add the penalty value C, for that row, F value changes. F1 plus C into A1. So here it is added to this first row. So first row F changes. This becomes F1 plus C into A1. There is no C value in the second row. So say F2 remains as it is. So there is a C value in the third row. So here F3 changes to F3 plus C into A2. Sorry, C into A3. F3 plus C into A3. Is this clear? Now reaction forces is found out using the relation Ri is equals to minus C into Qi minus Ai. Or in simple, just multiply this negative inside the bracket. Ri is equals to C into Ai minus Qi. So reaction you can find out directly here in the penalty method. I think this should be clear with the penalty method, how to solve it. So you will understand this in more detailed way by solving a numerical problem. Okay. So we will move on to this first numerical using penalty method. Okay. So first problem, the penalty method. So this is a step bar problem which is fixed at both the end, and material is different. This is steel and this is copper. Load of 100 kilonewtons applied at the fifth section. Diameter of first section is 60 mm. Diameter of the second section is 40 mm. Young's modulus of steel and copper is given 200 GPa and 100 GPa correspondingly. Okay. So already we have solved this problem in elimination method. You can go back and check our previous videos. So now we will solve the similar problem in the penalty method. Okay. So here, finite element model. First write the finite element model. Just write the nodes and the elements. Fixed, I need a node. Change in the cross section, I need a node. Fixed, I need a node. Okay. Number it 1, 2, 3, elements 1 and 2, and the force of 100 kilonewton is applied here, that is 100 into 10 power 3 Newton. So here in the penalty method, okay, similar in the elimination method, write the displacement in the forces. Displacements Q1, Q2, Q3, forces F1, F2 and F3. But unlike in the elimination method, like you used to write Q values and the F values, in the penalty method, please don't write Q values and the F values. Just write Q1, Q2, Q3, F1, F2, F3 and just leave it. I'll tell you why we have to do like that. Next, area of cross section of the first and the second. A1 is equals to pi by 4 d1 square, that is 60 60 square. So you'll get A1, and similarly A2, this is 40 square, you will get A2. Okay, next is element connectivity, elements and nodes 1 and 2. First element is between the nodes 1 and 2, second element is between the nodes 2 and 3. 1, 2, 2, 3. Next, element stiffness matrix for bar. So element stiffness matrix K is equals to AE by LE, 1 minus 1 minus 1, we know that. Next, for the first element, K1 is equals to A1 E1 by L1, that is 1 minus 1 minus 1, 1. Just substitute the values. Substitute the values. K1 is equals to substitute A1, E1 and L1 values. From the question you can see A1, then E1 and L1. This is the length of the first element. Okay. Just substitute the values. 1 minus 1 minus 1, 1. K1 is equal to 10 power 3 into the, take 10 power 3 as common, multiply everything to the inside. And the first element is between the nodes 1, 2, 1, 2. Just number it for your understanding. Similarly, for element 2, K2 is equals to A2 E2 by L2, 1 minus 1 minus 1, 1. K2 is equals to A2 E2 by L2, 1 minus 1 minus 1, 1. 10 power 3 common. Multiply everything to the inside. Second element is between the nodes 2, 3, 2, 3. Okay. Next is global stiffness matrix. K is equals to K1 plus K2. So here the size of the global stiffness matrix would be 3 cross 3 because there are 3 nodes. Okay. Just number 3, 3. And just write the elements. That is 1, starts from 1, 1. There is 1, 1 here. So this will be your first stiffness matrix K1. Okay, next second one starts from 2, 2. So where is 2, 2, 2, 2 is here, just this one. So this part is added here. Okay, very simple one like our previous problems. Next, finite element equation. We know finite element equation is KQ is equals to F. KQ is equals to F. So just write it. We have the K matrix K, Q1, Q2, Q3, F1, F2, F3. Just write as it is. Don't write Q1 as 0, Q3 as 0. Because in the penalty method, we will get all the values. That is Q1, Q2, Q3, all the thing we'll be getting it in the solution. Okay. So next, so using penalty method. So using penalty method of handling boundary condition. Penalty value C is equals to maximum of Kij into 10 power 4. So what is this maximum of Kij? So if you go back to this matrix, okay, so if you go back to this matrix, what is the maximum value in this, in the stiffness matrix, that is K matrix? What is the maximum value? We have 706, we have 958. So 958.1 into 10 power 3 is the maximum value. Okay. So maximum of Kij is 958.12 into 10 power 3 into 10 power 4. Okay, so we have got the C value. Okay, now as node 1 and 3 are fixed, C is added to K11 and K33. So we can see in the question, node 1 and node 3. Node 1 and node 3 is fixed. So C value should be added to the principal diagonal elements of node 1 and node 3. Okay. So here C value. Okay. Next, boundary conditions are. So here boundary conditions. So A is just taken as like a displacements, like we take it Q1 and Q3. Okay. But different notation. You will understand why we have used a different notation here, because we are adding it to the force values. Okay. So here it is fixed. So it is 0. A1 is equals to 0. Even here it is fixed. So there won't be any displacement. So A3 will be equals to 0. So boundary conditions, A1 is equals to 0. A3 is equals to 0. Modified equilibrium equation is given as, so 10 power 3. So equilibrium equation, this equation. So this equation is modified now. That is, we are adding C values to this one and this one. Okay, understood? Because this is a principal diagonal element and node 1 and node 3 is fixed. Okay, so since node 1 and node 3 is fixed, C value is added to the principal diagonal elements of node 1 and node 3. So if I add 706, if I add 958.1 to 706, I'll get 166.4 into 92.92 into 10 power 4, 10 power 3 common as it is. Similarly, add to this third one, add to this 251, I'll get 1209.44 into 10 power 4. Rest all the thing remains same. Rest all the thing remains same as it is in the K matrix. Okay. Now write Q1, Q2, Q3 as it is. What will be the F equation? F also changes. F1 and F3 changes because the first node and the third node is fixed. So what will be the F equation? F1 becomes F1 plus C into A1. Okay. What is F1 plus C into A1? F1 is, there is no force given there, so F1 is 0. Plus C is 958.12 into 10 power 7. A1 is 0. So whole thing becomes 0. Similarly, what is F2? F2 is the known force value which is given in the question. So F2 is as 100 into 10 power 3 Newton in the positive x-axis. So 100 into 10 power 3 Newton. And F3 is F3 plus C into A3. Okay. Why F3 plus C into A3? Because it is added to the third node. The third node is fixed. Okay. So A value should be added to the third node. So now A3 is 0. So even this becomes 0. Okay. Now multiply this matrix and try to solve this equation. So 10 power 3 common, row into column multiplication, 166.9 into 10 power 4 into Q1 minus 706.8 into Q2, 0 into Q3 is 0 is equals to 0. Similarly, this one minus 706.8, 10 power 3 are common, minus 706.8 into Q1, 958.12 into Q2, minus 251.32 into Q3 is equals to 100 into 10 power 3. 10 power 3 common, 0 into Q1 is 0, minus 251.32 into Q2, plus 1209.44 into Q3, 10 power 4 into Q3 is equals to 0. Solve these three equations in your calculator, you will get Q1, Q2 and Q3 values. So we have found the displacement Q1, Q2 and Q3 values. Now you might ask, Q1 and Q3 is fixed, so the displacements at Q1 and Q3 should be 0. Of course it is 0. So you can see here it has come into 10 power minus 6. So it is 0.00000, that is 6 zeros, 769. It is almost equals to 0. Even Q3 is fixed, so you can see it is also 10 power minus 6. It is almost equals to 0. Only Q2 will have the displacement of 0.104 mm. You can cross check this answer with elimination method, how we have solved in the previous class. Next, finding the reaction is very simple in this. To find reaction forces, we know that Ri is equals to C into Ai minus Qi. So R1, there will be two reaction forces, node 1 and node 3 is fixed. So R1 and R3 will be the reaction forces. R1 is equals to C into A1 minus Q1. Just substitute the values of A1. A1 is 0. C is this one. A1 is 0, Q1 is minus 7.69 into 10 power minus 6. So you'll get R1 is equals to minus 73.679 into 10 power 3 Newton. Similarly, R3 is equals to C into A3 minus Q3. So R3 is equals to C A3 minus Q3. You will get R3 is equals to minus 26.156 into 10 power 3 Newton. Okay. So this is the penalty method of handling boundary condition. We'll move on to the next problem using the same penalty method of handling boundary condition. We have solved even this problem earlier using elimination method. So now we'll solve using penalty method. So we have a step-up bar which is fixed at one end. In the previous problem it was fixed at both the end. So C was added to node 1 and 3. Here it is fixed at only one end, so C should be added only to this node 1. Very simple than when compared to the previous problem. So E1, A1 of the first cross section is given, E2, A2 of the second cross section is given, E values is given here, and even the A values is given. Length is given of both the bars, 50 and 50 of both the steps of the bar, and compressive load of 10 kilonewton is applied here. A tensile load of 5 kilonewton is applied at this point. At the finite element model, node 1, 2, 3, force of 10 kilonewton, force of 5 kilonewton, element 1 and 2, displacement and the forces, displacements Q1, Q2, Q3, forces F1, F2, F3. Don't write any values here because you will get all the values once you solve using penalty method. Okay. So next, element connectivity. Elements and nodes. So the first element is between the nodes 1 and 2, second element is between the nodes 2 and 3. Next, element stiffness matrix. Ke is equals to Ae by Le, 1 minus 1 minus 1 1. For the first element, K1 is equals to A1 E1 by L1, 1 minus 1 minus 1 1. K1 is equal to substitute the values of A1 E1 and L1, 1 minus 1 minus 1 1. 10 power 3, keep it as common, take everything inside, you will get 600 minus 600 minus 600 and 600. So first element is between the nodes 1 and 2. So just write 1 2 1 2 for your understanding. Okay. Next, second element. For element 2, K2 is equals to A2 E2 by L2, 1 minus 1 minus 1 1. K2 is equals to A2 E2 by L2, 1 minus 1 minus 1 1. Substitute the 10 power 3 common, multiply everything to the inside. Second element is between the nodes 2 3 and 2 3. Just substitute its values. Next, the global stiffness matrix. Ke is equals to K1 plus K2. So we have 3 nodes here. 3 nodes here. The size of the global stiffness matrix will be 3 cross 3. Write 3 cross 3 global stiffness matrix. And for the first element is in the coordinates 1 and 1. Just search for 1 and 1 in the global stiffness matrix. 1 and 1. So just write the first matrix. Similarly, the second matrix is between the coordinates 2 and 2. 2, 2. Starts from here, goes on like this. Okay. Next, finite element equation. Kq is equals to F, 10 power 3. Write this K equation. Q, write as it is. Q1, Q2, Q3, F1, F2, F3 as it is. Okay. Next, penalty method. So using penalty method of handling boundary condition. So using penalty method of handling boundary condition, penalty value C is equals to maximum of Kij into 10 power 4. So find the maximum value in this stiffness matrix. What is the maximum value in the stiffness matrix? We have 600, we have 750, 740, we have 140. So maximum value is 740. Okay, so maximum of Kij is 740 into 10 power 3. So 740 into 10 power 3 into 10 power 4 is the C value. As node 1 is fixed, C is added to K11. So I have said you in the earlier itself, here node only 1 is fixed. Only the first node is fixed. So K value is added only to the first node. So K value should be added only to the first node. And boundary conditions are A1 is equals to 0. The first node is fixed, so A1 will be equals to 0. Next, the modified equilibrium equation is given as so add C to this K11. So if I add C to this K11, I'll get 740 into 10 power 4 minus 600, 0. So add C value to this first K11. So if I add 600 into 10 power 3 plus 740 into 10 power 7, I'll get 740 into 10 power 7. So 10 power 4 here and 10 power 3 common as it is. Minus 600, 0, everything remains same. All other things in the matrix remains same. Q1, Q2, Q3. And F value, only the first one changes because C is added only to the first. So this becomes F1 plus C A1. A1 is 0, F is 0, so this thing becomes 0. And rest F2 and F3 is given in the question itself. F2 and F3 is given in the question itself. So write F2 and F3 as it is. So just multiply the equation, this into this. So just multiply the equation, 740 into 10 power 4, 10 power 3 common into Q1 is equals to minus 600 into Q2 into 0 into Q3 is equals to 0 is equals to 0. Similarly, other three equations, 10 power 3 common, minus 600 into Q1 plus 740 into Q2 minus 140 into Q3 is equals to minus 10 into 10 power 3. 10 power 3 common, 0 into Q1 is 0, minus 140 into Q2, 140 into Q3 is equals to 5 into 10 power 3. So we have three equations and three unknowns. We will get Q1, Q2 and Q3. You solve the equations in your calculator, you will get Q1, Q2 and Q3. And you can see here the displacement values. The first node is fixed, so Q1 value is almost equals to 0. It is 10 power minus 7, so it is almost equals to 0. And Q2 and Q3 values is minus 8.33 into 10 power minus 3, and Q3 is minus plus 0.0273 mm. Okay. Next, to find the reaction forces, Ri is equals to C into A minus Qi. Only first node is fixed, so there will be only one reaction force. R1 is equals to 740 to 10 power 7. A1 is 0. Q1 is 6.7573 to 10 power minus 7. So R1 is equals to 5000.4 Newton. Okay. This should be clear, I guess. We'll move on to the next problem. Okay. We'll move on to the next problem. So here we have a bar given as shown in the figure. So from this point to this point where the load is applied, the distance is 150 mm, and from the load where the 16 kilonewton of load is applied, from that point to the end of the bar is 150 mm, and from the end of the bar there is a space, there is a restricted deformation, or there is a restricted movement of the bar. There is an empty gap, and after that there is a fixture. And that distance between the fixture and the bar is 1.2 mm, and the area of cross section of the bar is 250 mm square. Young's modulus is 20 into 10 power 3 Newton per mm square. Okay, so very different kind of a problem, and even a very important problem. It is asked many times in your university exam. So the nodes 1 is fixed, and the node 3 is fixed here. So you can write 1, 2, 3 and the elements 1 and 2. Displacements Q1, Q2, Q3, forces F1, F2 and F3. Only F2 force of 60 kilonewton, that is 16 to 10 power 3 Newton is given. Don't write any displacement values and any reaction forces at this point. Okay, so known or prescribed displacement. So A1 is a displacement at the first node. So first node is fixed, so A1 will be equals to 0. And second node, of course, there won't be, there will be some displacement, we have to find out. And the third node, A3. A3, you can see here, this node can move to certain distance. So that is, it can move to a maximum distance of 1.2 mm because of this load. Even if the bar is elongated, it can move only up to this distance. That is, it is fixed here. That is, the maximum displacement will be 1.2 mm. So A3 will be equals to 1.2 mm. Okay. So this is the only difference in this problem when you compare this to your previous problems. Okay. So next, everything as it is. We have the elements stiffness matrix. KE is equals to AE by LE, 1 minus 1 minus 1. Similarly, we have K1 is equals to A1 E1 by L1, 1 minus 1 minus 1. So K1 is 10 power 3 common. A multiply everything to the inside. We'll get 33.33 minus 33.33 minus 33.33, 33.33. And this is between the nodes 1 and 2. So 1, 2 and 1, 2. Okay. We've got K1. Similarly, K2 is equals to A2, E2 by L2, 1 minus 1 minus 1, 1, 10 power 3 common, multiply everything to the inside. We'll get K2, 2, 3, 2, 3 is between the nodes, 2, 3 and 2, 3. Now next step is only two elements. Next step is global stiffness matrix. So Ke is equals to K1 plus K2. So K is equals to, so 1, 2, 3 and 1, 2, 3. So the first element is between the nodes 1 and 1. So this will be the first stiffness matrix and this will be the second stiffness matrix. Only this part you have to add. Okay. So since we are solving using penalty method, in this matrix, try to find out the C value. So C is equals to maximum of Kij into 10 power 4. What is the maximum of Kij here? 66.66. So 66.66 into 10 power 7 will be the C value. Now add the C value to wherever it is fixed. So now if you go and look back to this question, node 1 is fixed and node 3 has a specific deformation and then it is fixed. Okay. So you have to add C value to node 1 and node 3 both. Okay. So add C value, the 66.66 into 10 power 7 plus 33.33 into 10 power 3 will get 66.66 into 10 power 4 and 10 power 3 as common as it is. So add C value to this principal diagonal element of this and this value, that is first and the third node is fixed. Rest all the values of K remains same. Q1, Q2, Q3, and since this and this is fixed, the force values also changes. The first becomes F1 plus C into A1. A1 is 0, so this whole thing becomes 0. F2 value is given 60 into 10 power 3 in the question itself. Okay. Similarly, F3, even this is given. A3 value is given. A3 is 1.2 mm, the known or prescribed displacement. This is 1.2 mm, the maximum displacement at this point. Okay. So here A3 into C. A3 into C is 66.66 into 10 power 7 plus F3. F3 is 0. Okay. So A3 into C will get 800 into 10 power 6. Is this clear? Rest everything is same. Matrix multiplication, this row and this column, that is 66.66 into 10 power 4. 10 power 3 common as it is. 33.33 into Q2 should be equals to 0. So here 10 power 3 common. Okay, please don't miss it. And even here 10 power 3 common, even here 10 power 3 common, this row into this column, this row into this column, this row into this column, similar how we have solved in the previous problems. So 3 equations and 3 unknowns. we will get q1, q2 and q3 values. Okay, so you can see we have got q1, q2 and q3. q1 is completely fixed, so to 10 power minus 5 it is almost equals to 0, and q3 maximum displacement is 1.2 mm and q2 displacement is 1.5 mm. Okay, next to find reaction, Ri is equals to C into Ai minus Qi. We have R1 is equals to C value 66.66 into 10 power 7. A1 is 0 minus Q1 is 7.50 into 10 power minus 5. You will get R1. Node 3 is fixed, so R3 value, R3 is equals to C into A3 minus R3, sorry, A3 minus Q3. So here you can see R3 we are getting it as 0 because there will be a slight displacement in that, so there won't be a reaction force. Okay, next sigma 1 is equals to E1 by L1 minus 1 1 Q1 Q2. Similar formula like you have solved in the elimination method. E1 and L1 values minus 1 1, multiply this and this, you will get sigma 1 value as 199.99 MPa. Okay, next sigma 2 is equals to E2 by L2 minus 1 1 Q2 Q3, multiply this and this, you will get sigma 2 is equals to 40 MPa. Okay, I think this should be clear. I'll give you one more problem. I'll just give you a hint of one more problem, and you should be able to solve this. I won't be giving you a complete answer of this problem. So we'll move on to the next problem. For the tapered bar shown, determine displacement, support reaction, strain and stresses using two element discretization. Okay, so here he has given a tapered bar and he has asked to find the displacement, reactions, strain and stresses. So once you find the stress, of course you can find the strain because you know the Young's modulus. Okay, Young's modulus is also stress by strain, so you can find out strain when you know the stress and the Young's modulus of a particular material. So now here he has not mentioned in which method to solve, either to solve using a penalty method or using an elimination method. So when it is asked like that, it is left to you to solve using any method, using penalty method or elimination method. It is left to your choice. Okay, but the steps will be same even for the penalty method or the elimination method, how we did in the previous problem. So here he has given a tapered bar. So area of this first cross section at this point, he has given A1 is equals to 1200 mm square, and A3 at this point is A3 is 600 mm square, 300 mm is the length, and the force of 1000 Newton is applied. Young's modulus E is equals to 2 into 10 power 5 Newton per mm square. So just write the finite element model 1, 2, 3, element 1 and 2. Okay. So before moving on to the next step, you have to find the area, you have to convert the tapered bar into a stepped bar and then you can solve it easily. Okay, in order to convert the tapered bar into a stepped bar, you have to find the cross sections area at this point. Okay, in order to find that, first find the cross section area at this point. This is A2. Okay, so A2 is equals to A1 plus A3 by 2 will give the cross section at this midpoint. So A1 plus A3 by 2, that is 1200 plus 600 by 2 will give 900 mm square. So A2 is equals to 900 mm square at this point. So if I want an area at this point, somewhere a uniform cross section at this point, I have to add this and this divided by 2, I'll get the area at this point, which is a uniform cross section. So area of the element 1, or to find the area of this element 1, A1 dash is equals to A1 plus A2 by 2. That is, I'll get area of this first element. So A1 plus A2 by 2, that is 1200 plus 900 by 2. I'll get 1050 mm square. Similarly, if I want area at this point, I will do A2 plus A3 by 2. So A2 dash, area of the second element, I'll get A2 plus A3 by 2, that is 900 plus 600 by 2. I'll get 750 mm square. Okay, I think this should be clear. Now convert that tapered bar into a stepped bar. So A1 dash is 1050 mm square, A2 dash is 750 mm square, 300, and a force of 1000 Newton is applied. E is equals to 2 into 10 power 5 Newton per mm square. So similarly, write the displacement and the forces Q1, Q2, Q3, F1, F2 and F3. Node 1 is fixed, so Q1 is equals to 0. Q2 and Q3 we have to find out because it is not fixed. There will be some displacements F1, F2 and F3. F1 is equals to R1 because it is fixed, F2 is equals to 0 and F3 is equals to 1000 Newton. So here I will be solving using elimination method. It is left to you to solve using elimination method or penalty method. And write the element connectivity 1 and 2, 1, 2, 1, 2, 3. So 1 and 1, first element is between the nodes, 1 and 2, second element is between the nodes, 2 and 3. Elements difference matrix K is equals to AE by LE, 1 minus 1 minus 1, 1. Write K1, A1, E1 by L1, 1 minus 1 minus 1, 1. 10 power 3 common, take multiply everything inside, so 1, 2, 1, 2. Similarly, K2, 750 into 2 into 10 power, that is A2, E2 by L2, 1 minus 1 minus 1, 1, 10 power 3 common, multiply everything inside. This is 2, 3, 2, 3. Okay, so this is 1, 2, 3, 1, 2, 3. This will be the first element and this will be the second element. Okay, so till here the steps are same. Next is KQ is equals to F. KQ is equals to F. You can use, this is an elimination method. You can use using an elimination method, or you can use a penalty method, that is C is equals to maximum of Kij into 10 power 4. So maximum of Kij here is 1200 into 10 power 7 will be the C value, and you can add to the first node of the principal diagonal element and then solve it. Okay, so this you can solve using any method, using a penalty method or an elimination method. So kindly go through this numericals, and you have to solve this numerical, and you can note down the final solution of this problem. Thank you so much, guys. Any doubt, you can comment on the comment section or you can call me. Thank you.